Module 4, Lesson 22, Writing and Evaluating Expressions, and this time we'll be looking at exponential expressions. Alright, so we've got our learning targets here. We are going to continue to do a little bit of experimentation, got a little bit of substitution going on, and we are representing real-life situations using mathematical expressions. I-can statements, we're going to write expressions with variables, and exponents, I'll get an and in there. And we're going to use substitution to evaluate for a given value of a variable. And we are looking at tables of values and representing the relationships on that table using exponents. Alright, so kind of fun activity today. So you're going to want to actually do this on your own, so pause as much as you need to. How many times can you fold a piece of paper in half? And we're going to have the folds be as close to half as possible, and we are also going to fold in the same direction because we need to be able to do some counting. So make your prediction and record it. No peeking, no jumping ahead. Alright, and now we're going to start looking at some mathematical representation of what happens here. So before any folding, before we have 0 folds, there's one layer. You got a layer of paper sitting there on your desk. And we record this in the first row. And we're going to look at it exponentially because, of course, we're working with exponents today. And if we want to show that we have one layer and we are using a base of 2, we have 2 to the 0 because the 0 power means 1. So now fold your paper in half and you will have one fold. And record how many layers you now have. Got 2 layers, and write that in exponential form with a base of 2. So I have 2 to the first layers. Fold the paper again. Remember, we're folding the same direction every time. So now we've got 2 folds, and you should be able to count the corners. If you're folding in the same direction, if you look at one of the corners that's loose, you should be able to go 1, 2, 3, 4. And there are 4 layers, which would be expressed as 2 to the second power. I'm not going to write all of these down, but what I'd like you to do is pause the video, go ahead and complete as many folds as you can. Remember, we want these to be folds that are in half, not partial folds. We want nice, good folds. And figure out how many layers that there will be. I know in your materials that your rows go far beyond the 8 that I have on my page here, but that's okay. So pause and take care of that, and when you're ready, unpause and continue. Alright, so here's a question. Are you able to continue folding the paper indefinitely? Meaning, can you just keep folding in half? Just keep on going. Well, no, it's not going to work. The stack is going to get really thick because you keep doubling up. You probably got to a certain point where you're like, I just can't even fold it, and it's not in half anymore, and it's really messy. So take a look at your table compared to my table, and I know that I stopped at 8 folds here, and you went on to probably 14. Which is great. So how could you use a calculator to find the next number in the series? Whether I'm at 8, whether I'm at 14 layers, how do I find the next layer? What are we doing each time? Well, we're multiplying by 2 each time. So if I stopped at 8 and I wanted to find the next layer, I would multiply by 2 again. Each time multiplying by 2. Repeated multiplication. We're multiplying over and over again. Sounds like exponents. So the relationship between the number of folds and the number of layers. So the relationship here, number of folds, to the number of layers. Got a little excited there. Folds to layers. What is the relationship here? Well, as the number of folds increases by 1, the number of layers doubles. So we added 1, but we doubled. Added 1, but we doubled. Added 1, but we doubled. This is an exponential relationship. And we represent it in exponential form by increasing the exponent by 1. So by adding 1 to the exponent, and then having a base of 2, we are showing to add 1 more doubling. So plus 1 here, so we've got an exponent of 1, we've got an exponent of 2. So we added 1, but 1 of what? 1 of a times 2. So we could use 2 as the base, because that's our doubling. And we add 1 to the exponent, because that's the double it 1 more time. So if we fold the paper f times, so now we're going to a general situation here. Write an expression to show the number of paper layers. So we've got very specific examples that we've looked at, and now we're saying how could we find out how many layers for any number of folds? Well, if we paid attention on the last slide, we've got 2 raised to the power of f. And remember that chevron symbol there is an exponent symbol. All right, so here's an extension question. What if we were, instead of folding the paper, what if every time we were going to fold it, we cut it in half so we could pick it up and stack it on top? And then we cut it in half again and we stick it up and we put it on top, so that we could keep going. So write an expression that describes how many layers of paper would result from 16 cuts. If we had a piece of paper and we kept cutting and we did it 16 times and kept stacking them up, how many layers of paper would we have? Well, we would have 2 to the 16th. We're cutting, doubling, cutting, doubling. And go ahead and evaluate this expression by writing it in standard form. And if you need to use a calculator, that might be a good idea. So we've got 2 to the 16th, or 65,536 layers of paper. That's a pretty good sized stack of paper. All right, another common example dealing with exponents is bacteria. Bacteria are little single-celled organisms, and they reproduce in a couple of different ways, one of which is called binary fission. So the bacterium, which is a singular for bacteria, it grows until it splits. So one of them grows and splits into 2 of them. And then the 2 grow and split again. So you can see we have this doubling going on. And so we're multiplying by 2 over and over and over again. And when we multiply by 2 over and over and over again, we have exponential growth. We have exponents involved. So our next example looks at the growth of bacteria. All right, so you've got a table in your workbook. Go ahead and record the number of bacteria that result from each generation. So if I've got 4, each of the 4 splits. Oh, sorry, start at the 1 here. I've got 1, and it splits. So I've got 2 bacteria, which is 2 to the 1st. The second generation, so now I've got 4 of them, and they all split, and they turn into 8. And I've got 8, and they all split, and now I've got 16, which would be represented as 2 to the 4th. Now all 16 of them split, and that turns into 32. So that's 2 to the 5th. So go ahead and complete out your table here. I'm not going to sit and do all that for you, but go ahead and finish out your table here, noticing we're multiplying by 2 each time we go. So the question here is, how many generations would it take until there were over 1 million bacteria? We got to the 11th generation, and we've got 2,048 bacteria. How many times is this process going to go on until you have 1 million bacteria? So continue extending your table out until you find that. If you need to, use a calculator. And you will find out that it will take 20 generations to get more than 1 million bacteria. 2 to the 20th gets 1,048,576 little bacteria. Now, you might think to yourself, oh, 20 generations, that takes forever. Well, under the right conditions, many bacteria can reproduce every 15 minutes. So they are doubling every 15 minutes. So under those conditions, how long would it take for one bacterium to reproduce itself into more than 1 million bacteria? So if you stop and think about this, you start, we'll call it at 0 minutes, you've got one bacterium. 15 goes by and you've got 2. 30 goes by and you've got 4. And 45 goes by and you've got 8. 60 goes by and you've got 16. Now, if you're kind of paying attention here, you will notice that some of this ties to this generation stuff. So here's the first generation, which starts at 0 minutes. The second generation is at 15. Third generation is at 30. Fourth generation is at 45. Fifth generation is at 60. So you can add a column to your table and keep counting out here. And as you do that, once you get down to that 20th generation, you're going to find out that it's going to take 20 15-minute periods, which is the same as about 5 hours. If you wonder why it's important that you wash your hands, you get one little bacteria on you and you don't wash it off, and it has the right growing conditions, so it gets in your nice, warm, moist body where things like to grow. Within 5 hours, in the right conditions with the right bacteria, you could have 1 million little bacteria growing in you. Wash your hands. All right, so write an expression for how many bacteria would be present after G generations. So right now we have a very specific situation. Let's expand that out to any number of generations. How would we express that mathematically? Well, hopefully you have figured out that it would be 2 to the G bacteria, because we're doubling, and G is the number of generations. All right, going to take a look here at a special situation with a rectangular prism. It's important to recognize that the rectangular prism that we are looking at here is a special case. We are going to have it set up in a ratio of 1 to 2 to 3. Not all rectangular prisms have this ratio. So please do not believe that every rectangular prism you ever see after this is the same as this rectangular prism. And so they're going to say here we have a ratio of 1 to 2 to 3. So we've got the length, the width, and the height. And it's a ratio of 1 to 2 to 3. And that should, in your brain, say that, okay, the width is double the length and the height is triple the length. 1 to 2 to 3. To find the volume, we would multiply the length times the width times the height. That's the basic formula for volume of a rectangular prism. Length times width times height. So if we were to look at this particular example, the length comes in at 3W, so we would substitute that in. The width stays as the W, so we would substitute that in. By the way, I got my ratio just a little bit wrong because I had length, width, and height. The width is the 1, and the height is the 2, and the length is the 3. But I'm pretty sure you saw me do that, and you're like, okay, I understand what he did. He just wasn't being careful. Oops. And then the height is going to be 2 times w, so we substitute that in. So now we are left with this multiplication expression, and I would like you to notice that it has been separated out into the separate factors. This 3w became a 3 and a w, and this 2w became a 2 and a w, and it was recognized that this is multiplication, so we can use the commutative property and change the order. So we get 3 times 2, which gives us the 6, and then we've got these w's that are multiplied 3 times, an exponent. Remember that chevron symbol is an exponent. So we're going to use our special case here and play with a table of information. So we have the width, height, and length. Width is 1, height is 2, and length is 3. A ratio of 1 to 2 to 3. So if the width is 1, what is the height? Well, the height's a 2. We've got a ratio of 1 to 2. If the width is 1, the length is 3. We've got a ratio of 1 to 3. And the volume, we multiply them together. 1 times 2 times 3 gives us 6. And we've already put a label here that it will be cubic centimeters, so we don't need to add all of that here. I added an extra row to my table because I'm going to represent it as the width, and the height is going to be 2 times the width, and the length is going to be 3 times the width. All right, so if the width is 2, the height is double that, it would be 4, and the length is triple that, it would be 6. Multiply together, I've got 8 times 6, which gives me 48. So take a few minutes, pause the video, go ahead and complete out your table. And when you're ready, go ahead and unpause that. I'm not going to fill all of this in for you. I'll let you do some of this work yourself. And you'll notice that my top row now corresponds with my bottom row. And I'm going to get an expression here where I have 2 times 3, and I've got w multiplied together 3 times. So I have 6w cubed. All right. So why is 5 to the 3rd power different from 5 times 3? I've ranted and raved in my classroom about this. When we raise a number to an exponent, we are multiplying over and over again. When we multiply, we are adding over and over again. Adding over and over again is not the same as multiplying over and over again. This would give me 125. This would give me 15. Clearly not the same stuff. 5 to the 3rd means multiply 5 3 times. 5 is the factor that will be multiplied by itself 3 times. That's 125. On the other hand, 5 times 3 means we're going to add 5 together 3 times. 5 is the addend. We're going to add it to itself 3 times. That only gives me 15. Exponents is not the same as just regular multiplication. Please stop thinking that. And of course, you know, there are some problems where it works out really well. Like everybody loves 2 squared because that's the same as 2 times 2. But that creates a false idea that you can just multiply the base by the exponent. You can't do that. All right, quick look at the I can statements here. Representing real-life situations by writing expressions, variables, and exponents. Substitute to evaluate expressions, did some of that. And then write an expression to represent the relationship on a table of values. We looked at examining for exponential relationships within tables. Learning targets. We experimented, we did a little substitution, and we represented real-life situations. We did have a review there at the end, the relationship between multiplication, addition, and exponents. So that concludes Module 4, Lesson 22. If you've got questions, make sure you get with your teacher and make sure you complete your problem set.